robot reproduction, as explained by the grandfather of the first robot baby. I'm Tonya Hall for ZDNet and Tech Republic, and joining me is Gusz Eiben, professor of artificial intelligence at Vrije University in Amsterdam. Welcome, Gusz.
Good evening, Tonya. Thanks for having me.
No worries. So, give us a brief summary of your work and in artificial intelligence and robotics.
My work in artificial intelligence is a bit specialized. It's not the mainstream AI. I would like to build embodied intelligence. So you have the digital intelligence, which is all about thinking machines. And my research vision is to build acting machines. And I also have a very clear opinion about how to build them based on observing evolution in nature. And my one sentence research motto is considering that evolution can produce intelligence, and you and me are part of the evidence of that. It is very reasonable to assume that artificial evolution will create artificial intelligence. And because I would like to make embodied intelligence, it brings me to evolving robots.
In 2016, you were a part of a team of scientists at the Vrije University in Amsterdam that demonstrated how robots can reproduce. How do you define robot reproduction in that project?
Oh, that's a very good one. It's a very biological definition. So the way we define robot reproduction in this experiment and in all my work is you could claim or you could state that a robot is an offspring of one or two other robots if is basic genetic material, the code, the DNA, if you will, is a variation of the one single parent, in which case we call it a mutant, or if the new robot is based on a mixture of the DNA, the code of the parent robots. And if this is true, then it satisfies the definition which we also use for animals or peoples on the globe.
You identified two lines of research related to the evolutionary robotics. Tell us about both the software and the physical.
So the software part is digital evolution, which is a stream of research and development, which was already started in the 60s, 70s of the 20th century. It started with trying to implement Darwinian principles, survival of the fittest and reproduction, mutation, natural selection in virtual worlds, in computer worlds. And that has become a very interesting research field known under the name evolutionary computing. That's extremely interesting. It can solve problems that human optimizers or designers cannot solve very easily. It can bring us excellent solutions and also very original, unexpected solutions because it is not constrained by the human rules of design and optimization and symmetry. So that's a proven area which I have been working in for 25 years. And at a certain moment, I wanted to have a new challenge. And I couldn't think of any bigger challenge than liberating artificial evolution from the computer and bringing it out of virtual digital worlds and making it physical. And when I started to develop the idea and thinking about what it really meant and how it could be done, I realized that the evolution of things, as opposed to the evolution of digital code, could be also applied to the evolution of coffee mugs or the evolution of pens or the evolution of t-shirts, which is interesting on its own. It would be evolutionary design. But these objects are not animated. They don't do anything. They just are. So you could evaluate and use the survival of the coolest to t-shirts or coffee mugs. But because they are not animated and actuated, it's less interesting than the evolution of animated, actuated objects, which are known under the name of robots. So this was the birth of the idea of, okay, let's evolve robots in the physical reality. And not only their brains, which has been already done in the area of evolutionary robotics, but also their bodies. So morphological evolution, body evolution, physical evolution of robots that will produce offspring, children and grandchildren and great-grandchildren in the physical world. So that was the concept. So that's what started to fascinate me. Could it be done, and how that could be done? And the how question was, for a long time unresolved in my mind. I could look at evolutionary robotics in the digital realm, in computer simulations. There is very interesting work, very inspiring work, but they didn't solve the main problem, how to become physical. And then I had two ideas which basically solved the problem. One was we can use 3D printing technology. In common parlance, putting it very, very popularly and simply, the 3D printer is the womb. If we had the 3D printer technology, which could spit out a fully functional robot with all the moving parts, all the electronics, all the CPUs and the cameras and all the servo motors, then we could really use that as the production facility, the birth clinic, if you will. And then it would solve the birth problem. And the other thing that I solved also, that it was hand in hand going with this, is we should and could and will make the same distinction between genotypes and phenotypes that we have in the animal kingdom. All animals, including the Homo sapiens, like you and me, first were a specification, a code. That's the DNA of your father and your mother. And they recombine their DNA, and that gives us a new specification sheet, a new description of some individual that didn't exist beforehand. And then it took 9 months to go from the genotype to the phenotype. The biologists say to express the genotype and produce the physical entity that is encoded by that. And I said, this is exactly what we will do for robots. And the robotic genotypes will be specification sheets, digital code, which we know from evolutionary computing. And the 3D printer will be used to express the genotype into a phenotype and produce a physical robot encoded by that piece of DNA. And one more thing to that. So the biological analogy does not stop here. Just like in biology, it's really important that the mutation and the crossover always apply to genotypes. As you know, it's not like my father gave me an arm and my mother gave me a leg. They combine the DNA, and the mutations and the crossovers always take place at the level of the genome. And selection, the judgment of the environment and your fellow animals or possible mating partners and your food and the predators that want to eat you, they all evaluate your phenotype, the way you look, how quickly you can move, how well you can hide, how intelligent or how strong you are. So I decided also that we should maintain this dichotomy, and we will have a genetic language for robots where we apply mutation and crossover, and we have the robotic phenotypes which are produced by the 3D printer, which is where we evaluate them, see what they do, see if they are good, nice, lovely, useful, and then we will allow them to reproduce and have more children.
So let's take a step back. The mating process involved two robots meeting each other and deciding on their own that they favored each other. Explain how the robot dating actually worked.
It depends entirely, how the robot dating actually works depends entirely on the designer or the experimenter. It's the experimenter, in this case it was me and my collaborators, who established the laws of robot dating. And it would be very logical to say that two robots, they observe each other and they assess each other by certain features that are important for robots to survive. For instance, the level of energy. If your battery is fully charged, then you are probably a strong robot who can always find food, and then you would make a good mating partner. If your battery level is very low, then probably you are not so successful in surviving in this world. So I will not be very much inclined to have a robot baby with you. It could be related to something very user-defined or application-oriented. If the robots have a certain task, like collect garbage in a football stadium, then two robots that meet and mate, or before mating, after meeting, they could check each other, how many soda cans have you collected in the last 30 minutes? And if you have collected a lot of soda cans, that you are good for the task, so you are, possibly good father or mother of my baby. in the famous robot baby experiment, we defined the rules of mating, and because the experiment started with 2 robots only, we actually switched it off. So there was no choice for the robots. There was no space for being choosy. We made a system in which if they approached them to a certain distance, then mating happened. They didn't have a choice. So you could interpret it as a basic instinct. They followed their instinct, and none of them was saying, no, I don't like you enough. So they went for it. So that was the condition. And the act itself, it was not physical, actually. So there was no touching involved. It was simply by Wi-Fi. After the robots have decided that they want to have an offspring, they digitally, by Wi-Fi, they send their DNA, the specification sheet, to a computer, which was driving the 3D printer. And the computer combined the 2 pieces of robotic DNA, producing a new DNA with new features, more legs or fewer legs, longer legs or shorter legs, different colors, different setups, different position of the head. And that specification sheet prescribed how many new blocks we needed, how many new motors we needed, how many new cameras and CPUs. And the printer started to make the blocks. And because the 3D printing technology is not that advanced yet, it was not that advanced in 2015 and 2016, we needed a PhD student who removed the blocks and assembled the whole robot together.
Okay, we're a few years on now since the first
Yes.
family. How has this evolution of this experiment progressed over time? And, are we making better robot babies, or are they making better robot babies?
Yes, actually, we really broke through a barrier, because after this proof of concept experiment, we really broke through a barrier, because after this proof of concept experiment, I applied for research grants so that we can, scale up and make much better robot morphologies and much better production technology, produce better and more of them, so that we would have generations. And unfortunately, all these research proposals were rejected, mainly by the argument, this is science fiction, this is not science. This does not have an application. And they didn't buy my argument that it is also good for fundamental research into evolution and the emergence of intelligence. They didn't buy my argument that this would be good for breeding robots rather than designing and constructing robots for some environments where we don't know the optimal robot solution. And unfortunately, 2 or 3 proposals were turned down after that, until a colleague from the UK, from the University of York, and Professor Andy Tyrrell, who got me there as a visiting professor, succeeded in making a British consortium plus the Vrije University at Amsterdam and myself, who put in a research proposal that was granted. And Andy did 2 things very well. He made a very big, very nice consortium that covered all the necessary expertises, and he found an application. And in the UK, there's a huge problem, and that is they were too early with nuclear technology. So they are also very early in shutting down nuclear power plants. And there are, dozens of nuclear power plants that don't work anymore, and nobody knows what's inside. So obviously you have to send in robots, but we don't know what kind of robots. So the application that was very helpful in selling this proposal is we will evolve robots for exploring and decommissioning nuclear power plants. And this was granted in 2018, so about half a year ago the project started with a 2 million grant, 4 universities, altogether 15 people who are really working to build a much, much better birth clinic or a much, much better robo-fabricator. I was visiting York last week and I saw the place already, it's already there. There is a plate on the door saying automated robot, there is a plate on the door saying autonomous robot evolution lab. All the 3D printers are already purchased. All the robot arms that we put together, robot babies are there. So in the fall, somewhere around September, we will have it all up and running, and a completely new kind of robot morphologies will be coming out at a speed of hopefully a couple a day.
This has a very Demolition Man feel to me. and how this whole concept evolves into the robots communicating with each other about making a baby, if you will. And so, as the grandfather of the first robot baby, what ethical questions should we consider before we take this infant technology any further?
The ethics of physical robot evolution is really, really paramount. To put it very shortly, don't start something that you cannot stop. So if you start with a system of evolving robots out there in the wild, then you have to make sure that you won't get runaway evolution, that you won't get increasingly large population of robots who are, evolving into something that is hostile or indifferent or, eating up everything around us. So this was from the ground up. This ethical question was from the very beginning a very important aspect to me. And I was thinking about it, discussed it with my research partners in the UK and wherever I went to discuss this, and we came up with a solution. And the solution is that we deliberately deny all kind of animal-like distributed reproduction systems, meaning that we definitely do not want to have the robotic equivalent of cell division. We do not want to have the robotic equivalent of eggs. We do not want to have the robotic equivalent of pregnancy, because all these reproduction systems allow distributed, uncontrolled, unsupervised reproduction. Instead, we deliberately choose for a system with one single unit of reproduction, which you could call the robot fabricator or the birth clinic or the 3D printer, if you will. And this single facility is, from the robot's perspective, a single point of failure. If this fails, then reproduction stops. From our perspective, this is the kill switch, the emergency switch. If we switch off this facility, then reproduction stops. And that means there will be no new robot babies, there will be no new robot generations. And we may want to collect all the robots that are out there, but at least there will not be more of them. So this is our ethics and safety-based measure to keep it from runaway evolution.
Gusz Eiben, professor of artificial intelligence at the Vrije University in Amsterdam. If somebody wants to connect with you, what's the best way they can do that?
So they can follow me on LinkedIn, they can follow me on Twitter, although I'm not tweeting too much. The best thing is to put my last name in a search engine, Eiben, E-I-B-E-N, followed by Amsterdam, hitting my professional webpage, and there you will have a lot of contact information.
Sounds good. And thanks again for joining on this interesting topic. If somebody wants to connect with me, you can do so right here on CBS Interactive at ZDNet or Tech Republic, or go to my website, tonyahall.net. Thanks for watching.